Swayam Prabha. Digital India. Educated India.
So, the last lecture I was talking about various probability distribution functions, uniform random variate, exponential and normal and so on. In this course, we also will like to generate random numbers based on a certain distribution to simulate a stochastic process. Okay, and so it's important to know how to generate random numbers as per an underlying distribution. So, so in this class I am going to talk about three types of random numbers. Uniformly distributed, random number, exponential, and normal random variate. So, we will specifically talk about some numerical algorithm by which we can create these random numbers, and the application of these random numbers we will see throughout the course. So, first we will talk about the uniformly distributed random number. In the range from 0 to 1. Okay. Anyone is aware of any method to create random numbers of 0 to 1? Yeah. Delta function. But delta function will give you what? I'm not talking about 0 or 1, I'm not talking about binary, I'm talking about any floating, any decimal point between 0 to 1, such that the choice should be independent. Okay, all variables are equally likely, all numbers in this range has to be equally likely. So, I want a random number generator that would give me sequence of random numbers such that each random number has equal weightage. That is what uniform distributed random number means. Okay. But any algorithm that we are going to develop to create this is going to be from a deterministic approach. Because of that, any random number generator that we create using a computer are called pseudo random numbers. They are not truly random number, there is a, we call them as a pseudo random numbers because they are not strictly random. Okay. And I am going to give a couple of algorithms and show how this works, starting from a deterministic formula, how you can create a random number generation. So, the first method is called multiplicative congruential method. So, here we write a recursive relation that xn is equal to some a x n minus 1 modulo m. Okay. So, this is a mathematical statement of random number generator. So, n is a sequence. Okay. We start with some seed value x naught. Okay. So, this is seed, this has to be provided to initiate the sequence. Okay. If you have used any random number generator in your project or in any of your assignments, you would see that you always initiate with the seed. any sequence have to be initiated by a seed. In this case, we start with the seed and then get the next sequence. Here we define two parameters. One is this parameter A, which multiplies the seed, and then this multiplicated number has to be operated by the modulo operator. When we say modulo operator, what it means is we take this number, divide by this number, keep the remainder. That remainder is assigned to xn. Okay. Then after this operation, we say u is xn by m. After this operation is done, the xn value that you get will always be less than m, because it's a remainder. And when you take xn by m, this number will always be less than 1. So thereby the value of u here will distribute equally between the range 0 to 1. Okay. Now the question is, how do we choose these numbers a and m? Of course, you want this m to be as large as possible. It depends on the memory of your processor, if it's a 32-bit or 64-bit, and see what is the largest number you can store, and that number can be assigned as m. And this a can be any number, and there's a lot of optimization has happened, how to choose this number for a given computer architecture and so. Okay. So typically what happens is, I think m for a 32-bit machine, something like m is equal to 2 power 31 minus 1, and a is taken to be 7 power 5, which is 16807. These are actually optimized variables. Optimal. Okay. Now you can see this m is the largest possible number you can store in a 32-bit machine, and because of that the sequence will be very large. If m is very small, the cycle with which these numbers repeat itself will become shorter. Okay. I will give an example. I will choose very small a number and m number, and you will see how the sequence will start repeating. Thereby, having m as long as possible, you can actually have a very large sequence before it repeats. Okay. That's the reason why we say these are pseudo random numbers. They are not real random numbers. Okay. They all have a cycle time, after which the exact sequence will repeat. Okay. So our hope is to keep that cycle time as big as possible, and by the time you do a simulation, you will not really encounter that repeating behavior. Okay. So I'll give some workouts example, just to see this, what I mean by cycling and repeating and all that. So let's take an example that I have a seed value of 5. Yeah. Sorry. It can be avoided by having, it cannot be really avoided because it's going to be set by the largest m value you have. Okay. So I'll go through this example first. I show you how the cycling happens and what's the implication of m and why the m has to be as big as possible. If you have a 64-bit machine, you can actually increase the cycle time even beyond. So here is an example that I can do simply here. We say that xn is equal to 3xn minus 1 modulo 150. Just an example. So I've taken m as 150 and the prefactor a as 3. Okay, and I've given a seed value of 5. Okay, so now we can see the sequence of the random numbers that we can generate from here as a test case. So first we get x1 is 3 times x0 modulo 150. So 3 times x0 is 15, 15 modulo 150 is 15. Okay. The remainder that you get after dividing by 150, that's the modulo operator. So we have created the first random number, which would be 15 by 150, which is 0.1. The first random number we generated is 0.1. Then we go to the next sequence. We say x2 is equal to 3x1 modulo 150. So here my x1 is 15 and 15 times 3, 45, and 45 modulo 150 is also 45. So my E2 is 45 by 150. So 0.3. So this is my second random number. And then we can continue this. I am going to get x3 as 3x2. So I get 135, and U3 is 135 by 150, and this is 0.9. So by the time I get the fifth random number, I am getting this number 15, and this basically goes back to here. Okay, so that means if I look at the sequence, I would have got 0.1 first, then 0.3, then 0.9, then 0.7, then 0.1, and from here onwards it repeats again. So that means you have only created about 4 random numbers, and after which it starts cycling, repeating. Okay, so this is not a very good algorithm because the choice of the parameter a and m are not good. Okay, so we are saying that by optimizing the value of m and a, you can actually increase this cycle time so long that by the time you do your simulation or whatever calculation you want to do, this never repeats. Okay, so any questions? Yeah. Approximation for a sine wave. Why do you say that? I mean, I won't call it as a sine wave. It's some sort of periodicity, you can say. Okay, not necessarily a sine wave. Okay, so it's basically cycle backs. Basically means that we are revisiting the same seed again and again. So the sequence repeats. So there is some sort of periodicity, not necessarily a sine or cos. One improvement one can do is to add a constant term to this. Okay, that's called mixed congruential method, by providing one more variable and then extending the life repeating sequence. Okay, so So in the mixed congruential method, all we are doing is we are adding an extra term in the recursive relation. Apart from the multiplicative term, there is also an additive term, and again one can optimize how large the C should be and how large A and M should be. Okay, so this optimization is a different research area itself. But if you have ever used MATLAB or any other software to generate random numbers, it could have actually used one of these approaches. Okay. So you can probably try this example. So you can take x naught as 3 and a as 5 and c as 7 and m as 200. Okay, and try to get a sequence of random number and see what is a repeating, what is a cycling number. Now once we know how to make uniformly distributed random number, this will be the starting point for creating random numbers of other kinds. Suppose if you want to generate exponential random number or a normal distributed random number, the uniformly distributed random number is the starting point. You're going to generate this uniformly distributed random number and then do some manipulation to get other distributed random number. So it's very much fundamental. Okay, I don't think of any random number that can be generated without a uniform distributed random number. Okay, so this is going to be very basic. So let's say if I want to look at the second exponential distributed random number, exponentially distributed random number. So this is the probability density function for the exponential random variable with a parameter lambda. So clearly you can see this x is a random variable which is not uniformly distributed. It has a weightage. The low value numbers are more likely to happen than the high values as per this. Okay, so now we want to generate a sequence of random number, and if I make a histogram of the probability of occurrence, it should follow an exponential distribution. That's what it means. I should be generating more of small valued number than the larger. Okay, and the dependent should be an exponential formula like this, and it is characterized by a parameter lambda. So the starting point for this is, so we want to ask generate random variable x that follows p of x. Okay, so that's the question that we want to pose. So to do that, what we first will do is we will write a cumulative function for this, cumulative distribution function. And we call this as f of x. This is the integral from 0 to, so here by the way, x is a positive valued value here. Okay, so from 0 to some x, we integrate p of x dx. Okay, so this is the cumulative function, and if you do this, you will see this is 1 minus e power minus lambda x. So this gives me the probability of having a value x or less by this function. Okay, so it will smoothly goes from 0 to 1. Then what we say is, we say that let x be the inverse function of some uniformly distributed random number. Because this function has to go from 0 to 1, I can write a function x as some inverse function of u, and from here we say that f of x is equal to u, a random number uniformly distributed, is equal to 1 minus e power minus lambda x. So from here what we are saying is, you can generate a uniformly distributed random number from 0 to 1 because the cumulative function goes from 0 to 1 continuously, and from here once I have this number generated from the previous example, I can solve for x, and that x would have actually distributed as per this. Okay, so this is called inversion method. So I'm going to invert this inverse this function. So I'll get x is equal to minus 1 by lambda ln of 1 minus u. So using the mixed congruential method or a multiplicative congruential method, we create a uniformly distributed random number from 0 to 1, substitute that number here, lambda is known, you would have generated 1x, and that x is an exponentially distributed random number. Okay, and we call this method as an inversion method. Sorry, there is no recursion. There is no recursion. If you want to get 10 exponential random variable, you would create 10 uniformly distributed random number variable and use those 10 variables to here and get the corresponding x value. There is a one-to-one mapping of the uniformly distributed random number and exponentially distributed random number. So if u is uniformly distributed, what about 1 minus u? Right? So I can actually even just write simply as u. By doing this, you have actually eliminated one arithmetic operation, and especially when you do a large set of simulations, how much time you save in minimizing your operation is very significant. So 1 minus u and u, they are same in terms of the underlying distribution is concerned. So you can write x is equal to minus 1 by lambda ln u. We don't need an recursive relation here because we have a distribution function, and I can write a cumulative function, and then I can approximate this cumulative function because it goes from 0 to 1, and for every generated random variable, uniformly distributed random number variable, I can get the corresponding exponential. Okay, the recursive relation is not necessary here. Now generating the next is generating the normally distributed random variable with mean of 0 and variance of 1. Okay, once you have that, you can always change the mean and standard deviation by simple mapping. Now there are many methods to do it, but I'm going to discuss one method called polar method. Okay, and instead of creating one normal random variate, I'm going to get a set of random variable. Okay, two random variate at every time I call this function. Okay, so I'll discuss that first now. So let's say we have two random variable x and y, okay, and both of them are normal random variables, and they both have 0 mean and variance of 1. Okay, so that's perfectly fine. Now what I can do, I can write a and we say that x and y are independent. Independent random variables. Okay, so now I may be interested to write what is the joint distribution of x and y. What can I say about this? What is the joint distribution of x and y? The product of the individual ones, right? So it's p of x into p of y. Because it's an independent random variable, I can write product of the individual ones. And we know the functional forms, right? So we can substitute that now. 1 by square root of 2 pi, sigma is 1, e power minus x square by 2. This is the normal distribution function with the 0 mean and unit variance for x. Similarly, I can write for y. What is the range of x and y? Minus infinity to plus infinity, right? Now you see here I have x square plus y square. This can be actually shown into a plot. So suppose this is x and this is y. Any random variable I create from here would be a point in this plane. A particular xy combination can be shown as a particular point, and then what I can do, the distance from the origin is nothing but square root of r square plus y square. Okay, so we call it d. I think I call it as a d square. I will use this as a d, and this is the distance from the origin to this point, which is x square plus y square. And then I can also define an angle here, theta. Okay, and so we say that theta or tan theta is y by x, and d is square root of x square plus y square, something like this. Right. So what we have done is two normal random variate can be represented by a two equivalent variable of the distance from the origin and the angle, the polar angle. So that's why it's called polar method. So we are trying to convert this xy linear coordinates into a polar coordinate with a distance from the origin and a polar angle theta. So now we are basically going to ask the question, instead of generating two normal distributed random variable x and y, instead of this, how about drawing two random variables theta and d. If I know theta and d, I can also specify x and y. Okay, so the problem of sampling x and y is cast into another problem of choosing two random variable theta and d. If I know this theta and d, I can find what is x and y, right? So so I think I have to do this a little bit differently here. In my notes, I have written this as d is equal to x square plus y square. Okay, so this is not necessarily a distance, but the square of the distance. Okay, so so basically we wanted to find the distribution of d and theta, and once I know that, from this equation I can solve for x and y. Okay, that's the argument. So the problem we are trying to ask now is how to generate a joint distribution of theta and d. What can you say about the distribution of theta and d? Are they dependent or are they independent? Huh? They are independent? Anyone thinks they are dependent? They are independent. Theta can be anything from 0 to 2 pi. I can have the freedom to choose. Then this d is the distance from the origin. So these are two independent variables. So it preserves the character of the original distribution that we wanted. Okay. So now all we need to do is get a joint distribution for theta and d. Once we get that, we go back here and then map for x and y, and we would have generated two random variable. Okay, so that's the concept. And the way to do that would be, in one of the class, I think I mentioned about the transformation of random variable. I'm going to invoke that property using Jacobian. Y to go to x and y. So like I said, the initial problem was to get two random variable x and y. That is the design problem. That's the prescription of the problem. That when you do a simulation and you want to generate a random variable which is normally distributed. Okay. What we are saying is, ultimately we are going to generate that, but instead of directly generating it, we are actually doing through this polar method. Okay. So So when you want to go from one distribution to another distribution, the mapping has to follow this Jacobian relation. Okay. So here we have got two variable on both sides. Here we have d and theta, here we have x and y. This Jacobian is nothing but the partial derivative of each variable with respect to the others. Okay. For example, here we are taking differential of d with respect to x, d with respect to y. Here theta versus x and theta versus y. So now from this relation here, we should be able to get all these derivatives. I will give the relation directly, but you can check. So dou d by dou x is 2x. Dou d by dou x is 2x, and dou d by dou y is 2y, and dou theta by dou x, I get this as minus y by d, and dou theta by dou y, I get this as x by d. Okay, this is something you can verify later. So then if I substitute in this Jacobian, what I have is 2x 2y minus y by d and x by d. So we get 2x square by d plus 2y square by d, and this is nothing but just 2. Okay, because you will get x square plus y square, that's nothing but d, so you basically get a factor of 2. So when you substitute that here, we say that P2 of x comma y, the joint distribution of x and y is nothing but 2 times the joint distribution of t and theta. So what I am doing here is I am writing P2 of d comma theta is nothing but I bring this 1 by 2 on the other side, I get 1 by 2, and then I have P2 of xy. P2 of xy is nothing but this 1 by 2 pi e power minus d by 2. Okay. Previously I would have written as P2 of x comma y, I wrote as this right. This is P2 of xy. So here 1 by 2 pi, keep it like this. This exponential term, I write this x square plus y square as d. Okay, and this factor of 2 comes because of this relationship I showed. Okay, so that's what this is. Now the way to look at this function is what is the distribution of theta? It's a uniformly distributed random number in the limit 0 to 2 pi. That is this function. It's a constant. What is this one? This is an exponentially distributed random variable with a lambda parameter of 1 by 2. So what we are saying is, instead of generating two x and y normally distributed, an equivalent problem would be to generate two random variable, one that is uniformly distributed between the limit 0 to 2 pi, another one is an exponentially distributed with a parameter of minus 1 by 2. Okay, now do we know how to generate this random number and this random number? We know that, right? I showed how to generate random number from 0 to 1. If you multiply by that number with a 2 pi, you would have created the range from 0 to 2 pi. So that's as easy as that. We can use the inversion method I discussed before to calculate or to get the exponentially distributed random number for d. Okay, so once we get those two, and all we have to do is go back here and solve for x and y. So we say that so this is actually p of theta and this is p of d. P of theta, this is a uniformly distributed in the range 0 and 2 pi. P of d, this is the exponentially distributed with parameter lambda, which is 1 by 2. Sorry? Yes, yes. There are two, not only there are two random numbers, but we also know the distribution. One is uniform, another one is exponential. So once I know this information, I can use two uniformly distributed random number from 0 to 1, and if I take one of that and multiply by 2 pi, I get theta, because theta is also uniformly distributed, except that the range is not from 0 to 1 but 0 to 2 pi. So I get this u1 or u2, and then I multiply by a factor of 2 pi, I would have generated theta in the range 0 to 2 pi. Then I have another random variable u1, and I use this for the inversion method. Lambda here is 1 by 2, here I had 1 by lambda, so 1 by lambda would have become just minus 2 here. Ln of, instead of 1 minus u1, I put 1, just u1. So you first create uniformly distributed random number 2, u1 and u2. With that you get another set, theta and d. After here we can get x is equal to square root of minus 2 ln u1 cos 2 pi u2 and y as minus 2 ln u1 sin 2 pi u. So you would have produced x and y. This relationship comes right from here. And this we call as a polar method or Box-Miller method. So next time when you call a Gaussian function or normal function in MATLAB to get normal random variate, this is what's happening inside. Okay, so going to select two random variable, one that is uniformly distributed, another one that is exponentially distributed, and then this mapping was done to get x and y. You always get in pairs. Even if you need only one, you can actually get two at every time you call this function. What is the advantage of Gaussian method? No, there is nothing advantage like. I'm just saying that I have a process that is governed by a Gaussian distribution, and I want to let's say Brownian particle. Okay, I have a Brownian particle. I want to predict where the position is, and the position of this random variable is normally distributed. So you have a process to ask, give me a sequence of random positions for the Brownian particle. That random position is actually normally distributed. If you want to simulate that trajectory, you need random number, and you generate the random number by this method. Okay. I'll be uploading this notes of this class, and in here I have shown an example of how to use uniformly distributed random number to calculate the value of pi. Okay, and there's a nice example you can go through. You take a square and you take a circle inscribing it, and see, you throw random number and you see how many times the random number falls within a circle. Okay, and the ratio of the total, the ratio of the number of random numbers inside the circle over the total will give you the area ratio, and that area ratio has a factor of pi, and from there you can get pi. Okay, so that example is something that I have given in the notes. You can go through. All right. Any other questions? Yeah. Yeah, one example, but I will as we go along the course, we see that there are so many other processes in which the normal random variable is the key, and you have to generate, you have to, so you have to have a function, you call the function, it should give you a random number. Now if you want to code it, this is how, you have a class? Oh, okay.